Let's start Chapter 7, Exponential and Logarithmic Functions. We're going to start our chapter off by graphing exponential growth and decay functions. An exponential function is any function where x is an exponent. We've had x as a base before, but now it's as an exponent. Our template will look like this. Y equals a times b to the x power. Now b represents your base, just like it did in chapters 5 and 6. In order for an equation to represent an exponential function, your base always has to be greater than 0. So we can't have a negative b value. As we think about the types of graphs we're going to get, we're going to focus on two options, growth or decay. An equation that's exponential is considered a growth function if your base b is greater than 1. It's representing a decay function if b is a fraction between 0 and 1. Now you might be wondering what that letter a is doing out in front. That's going to be a coefficient. So a is just a coefficient out in front. A is not a part of the exponent. All right, down below, let's focus on domain and range. We've spent a lot of time defining domain for equations. In an exponential function, domain still represents all the possible input values. So our variable by default is going to be x. Now, it doesn't really matter what your base is. We can raise a base to any exponent, positive, negative, 0, fractions, decimals, and so on. This means our domain default for these equations is going to be x equals all real numbers. Make sure you have that entire statement when asked to state the domain. And you'll be asked to do that for every graph we do. Something we haven't done for quite some time is range. And range is just what the other kind of part of your function would give you, the set of all output values. Now your range could be y, or it could be f of x, etc. Instead of using capital D, we're going to use capital R. To define your output variable or notation, what's going to happen here is we're going to have a greater than or less than symbol for our ranges. And the template is going to start off as greater than 0. As we change the equation, we're going to move kind of the boundary where the graph will approach but never actually cross. And that boundary is a line that we call an asymptote line. There's a unique word for us, asymptote, A-S-Y-M-P-T-O-T-E. A line that a function approaches but never crosses. And we're going to use a dashed line to represent our asymptote, our boundary line. And the graph that we draw can't cross over that line. Now, things that are going to give us changes in our asymptote are when we perform a transformation on our function. If we take our y equals ab to the x and maybe shift what's happening to our x value, that can move it left or right. And then if something's being added or subtracted after, that can move our graph up or down. So the x minus h is going to affect our input. Anything that's added or subtracted after is going to affect our output and ultimately affect that asymptote line. We're going to have 6 graphs ahead of us, everybody. And as long as you create the table and kind of write all the work that I do, your sketch of your graph can be pretty kind of straightforward. It doesn't have to be super detailed. Please write out the directions below. For each exponential function, state the domain and the range. Then, oh, that's supposed to be make. Oh, goodness. Sorry, everybody. That should be make, not ache. Make a table of values and sketch the graph. Now, we're not going to do inverses today, so we're only going to have one graph on each coordinate system. Again, write the domain and range, make a table of values, and sketch the graph. Let's start with the graph y equals 2 to the x power. This is an exponential function because x is the exponent. Now, as we think about the values to plug in, we're going to use that x as our exponent to kind of define our possible options. So we know our domain is going to be x equals all real numbers. We're going to plug in anything we want. So as we create our table, I'm going to give you a template of values to start with. So the numbers that I plug in right here are the numbers that I'm going to want you to use unless we shift left or right. So we're going to always use these values. And there's 5 of them. We're going to do -2, -1, 0, 1, and 2. That's just going to be the template of values that we plug in for x, and then we're going to have to calculate our output. But if we move things left or right, we're going to adjust these numbers. In this case, though, we're not. So if we take 2 to the -2 power, that's 2 to the -2 power, any negative exponent is found by taking the reciprocal of the base, and that would make it 1 over 2 squared, which is 1/4. -1, same idea. 2 to the -1 power is 1 over 2 to the +1 power, or 1/2. 2 to the 0 power, that's the 0 exponent property, is just 1. 2 to the 1st power is 2, and 2 squared is 4. Let's plot these 5 ordered pairs on our coordinate system. -2, I'm going to go 2 to the left and up just a little bit, 1/4. -1, I'll go up a little bit higher, 1/2. 0, 1, 1, 2, and 2, 4. So notice this is not a straight line. This is not a linear function. This is nonlinear. An exponential function is going to have a really, really small output value on this left-hand side. But then as x increases, you'll notice all of a sudden the graph really turns and gets bigger a lot faster. So that's an exponential growth function. And what ends up happening is as it kind of levels out, as the graph kind of levels out over on that left-hand side, I'm just going to get rid of that part of the graph that we don't need right there. As that graph levels out, it approaches the x-axis but doesn't actually cross over it. So what I'm going to do is I'm going to draw in a dashed boundary line like so. This is where maybe another color might be a good option. And that's going to be the equation y equals 0 as our boundary asymptote line. However, for the range, notice that the green line isn't going to cross over the orange boundary line because that's our asymptote line. That means for our range, we're going to say that all of our output values have to be greater than that boundary line. So this is the equation, but this is the range value. And that's it. That's what we're going to do today for exponential functions. However, we're going to try some more interpretations of this equation. In our second example, what happens if there's a negative out in front? Well, if we think about defining that y equals a times b to the x, the negative that's out in front really represents an a value of -1. And if we think order of operations, 2 to the x power, we're still going to evaluate that first, but then multiply by -1. What that means is our domain, again, our domain is always going to be this answer, x equals all real numbers. So we should be able to recognize, we'll get a free point there. That's easy to remember. It's just what's going to happen with our range. All right, so as we create our table, notice nothing's impacting the x coordinates. I'm going to use my template of values, -2, -1, 0, 1, and 2. Now, when we plugged in -2 last time, we got 2 to the -2 power, which was 1/4. But now we're going to do -1 times 1/4, which makes it -1/4. -1, when x was -1, it was 2 to the -1, and that was 1/2. But the -1 on the outside makes it -1/2. So notice what's happening with that negative in the original equation, what it's doing to our output values. If I plug in 0 for x, 2 to the 0 is 1, but -1 times 1, yep, you guessed it, made it negative. And then 2 to the 1st power is 2 times -1. And last but not least, 2 squared is 4, but times -1 equals -4. So over here, if you just create your x and y axis quickly, and we plot the 5 coordinates given, -2, now our graph goes below the y, or the x-axis. Oops, that's pretty too far down there. Just goes slightly below, and then -1, a little bit lower than that. 0 down to -1 on the y-axis, 1 down to -2, and then 2 down to -4. So notice those values reflected over the x-axis, and that's because A is negative. So what's going to happen is on that left-hand side, it's going to trend really close to the x-axis, but not actually cross over. And then it's going to hit those values over here on the right and drop down towards -infinity really fast. Let's go ahead and draw in that boundary line, just from left to right. It's going to be right on that x-axis again. So the equation of that asymptote line is y equals 0. But now notice, everybody, for the range, this time all the values on the graph are below the x-axis. So this means our function f of x has output values that are less than 0. And that's the equation f of x equals -2 to the x power. Question 3, g of x equals 2 to the x plus 1. Notice the x plus 1 is now the exponent. And what this is going to do is move everything 1 unit to the left. Remember, anything with x, we're always going to go in the opposite direction. So I'm going to write moves left 1. And that's going to impact our table. It's not, however, going to impact our domain. We can still plug in whatever we want. But to make the table, if everything's going 1 to the left, instead of starting at -2, I'm going to go 1 to the left and start at -3. I'm still going to use 5 values, but I'm just going to start at -3. That means I'll do -2, -1, 0, and I'll stop at 1. And we only pick 5 points because we really want to generate that curve kind of to the shape. And then from there, we just draw our arrows to the edges of our graph. All right, so watch what happens. If we plug in -3, we have 2 to the -3 plus 1. And -3 plus 1 is just -2. And we've already done this one up above. We got 1/4. And the next one, if we plug in -2, -2 plus 1 is -1. And again, we did that up above. That was 1/2. So there's definitely going to be a pattern here as long as we recognize how to create those 5 coordinates in our x column. -1 plus 1 is 0, and 2 to the 0 is 1. Plug in 0. 2 to the first is 2. And last but not least, plug in 1. And that gives us 2 squared, which is 4. Go ahead and plot those 5 coordinates on your graph and see if you can visualize the whole graph shifting 1 unit to the left. And there you have it. Again, notice that we're not going to cross over the x-axis on this one. Let's go ahead and draw in our asymptote line, that dashed boundary that we don't cross over. Make sure your graph supports that. That's y equals 0. I think I should have written that up above. For our domain then, our range, g of x, notice, has to be greater than 0. So if I look up above, I think I have to write that equation in there. I just want to make sure we have everything. Oh, no, I have that. All right, we're all set. All right, we're just going to slide over to example 4 then. P of x equals 3 times 2 to the x plus 2 power. Please write that down. Notice the x plus 2 changes our exponent. And if it's plus, it's going to move 2 units to the left. And that's going to impact our table. But again, the domain, x can be whatever it wants, all real numbers. As we create our table, now we just have to think about working our order of operations. Instead of starting at -2 like we did in question 1, if I go 2 to the left, I'm going to go all the way over to -4. And then just do my 5 numbers from there, -3, -2, -1, and now we're going to stop at 0. Now the 3 out in front is going to make all of our answers triple what they normally were. I'll show you how that works. If we substitute in -4, we've got 3 times 2 to the -4 plus 2 power, which is 3 times 2 to the -2, which is 3, that's a -2 right there, 3 times 1/4, which would equal 3/4. So we're going to have to plot -4 up 3/4. Keep going. Plug in -3. Now -3 plus 2 is -1. And 2 to the -1 is 1/2. These are all numbers that we've seen already. 3 times 1/2 is 3/2, or 1.5, if that's easier to graph. -2, substitute that value in. And that's going to be 3 times 2 to the 0 power, which is 3 times 1, which would equal 3. Keep going. -1 plus 2 would be 3 times 2 to the first. Oops, sorry. Getting ahead of myself there. 3 times 2 to the first, which is 3 times 2, and that goes all the way up to 6. Watch what happens when I plug in 0. If we do 3 to the 2, or times 2 to the 0 plus 2, that's 3 times 2 squared. Order of operations, 2 squared is 4, times 3 goes all the way up to 12. Clearly, that's going to be very much off of our graph. Let's plug in what we know. -4 up 3/4, -3 up 1.5, -2 all the way up to 3, -1 all the way up to 6, and then 0 is going to be all the way up here somewhere off of our graph. Now our curve is still going to follow that model like we've seen so far. We're going to keep going towards that x-axis, but we're not actually going to cross over it. And then as x gets bigger, notice how much bigger that graph gets faster. Definitely shifted to the left and got steeper at a faster rate, but it doesn't go below the x-axis, so let's draw in that asymptote line. Really quickly try to get that done, y equals 0. And then for our range, p of x is greater than 0. All right, we have 2 more. Question 5, y equals 2 to the x minus 1, but then a plain -3 after. Watch what happens with this description. If our exponent is now x minus 1, that means we're going to go right 1 unit. But then this -3 after does something totally different. It's going to move everything down 3 units. And that's also going to change our asymptote. We haven't had that yet. All right, for our domain, at least we know there's consistency there. X equals all real numbers. But when we create our table, if we're moving 1 to the right, instead of starting at -2, 1 to the right would be at -1. That's where I'm going to start my list of values, and then I'm going to use 5 ordered pair, or 5 numbers after 5 numbers total. So -1, 0, 1, 2, and 3. Go ahead and pause the video and see if you can generate the outputs for this list. Once you think you have it, press play and we'll graph from there. Okay, let's see how you did. I got -2 and 3/4, -2.5. Ooh, let's get that negative in there. -2, -1, and +1. Watch what happens when I connect these dots. Now my boundary kind of drops down, and then all of a sudden starts to turn and make its way up to positive infinity. But we're now actually not going to cross over that boundary line at -3. So I'm going to draw that in. Y equals -3 is the asymptote, and everything is above that. So for our range, y has to be greater than -3. The asymptote is always going to shift the same direction as whatever's being added or subtracted at the end. All right, everybody, we have just one more. Let's see if we can make it through. For our last example, I made our base a fraction. K of x equals 1/2 to the x power plus 2. I forgot to have the +2, I don't know, typed in there. I'm not quite sure why that didn't happen. But anyway, we're going to take it. Now this +2, notice, isn't with the exponent. So there's nothing with the exponent. The +2 means everything is going to move up 2. And that's going to change our asymptote. Anything added or subtracted at the end changes the asymptote. But not our good old trusty domain. We know that that's the same every time. And for this one, we can go back to our old templated values, -2, -1, 0, 1, and 2. So -2, -1, 0, 1, and 2. Plugging it in, we're just going to take all of our answers that we get and add 2 to them. Now watch what happens, everybody. If we have 1/2 to the -2 power, to make our negative exponent positive, we take the reciprocal of the base. So that's going to be 2 over 1 squared, which is just 2 squared, and that's 4. But then if I add the 2 that's on the equation, we get 6. And if we have 1/2 to the -1, that's the same as 2 over 1 to the +1, which is just 2, and 2 plus 2 is 4. All right, let's keep going. 1/2 to the 0 power is just 1, and 1 plus 2 is 3. 1/2 to the first power, I suppose I should put a parenthesis around there too. 1/2 to the first power is just 1/2, plus 2 is 2.5. And last but not least, 1/2 squared is 1/4, plus 2 equals 2 1/4. Okay, go ahead and plot these 5 ordered pairs and then we'll be done. If you take a look at the 5 points that we plotted, notice how the curve is kind of flip-flopped. Now it's bigger on the the left-hand side, but as you connect those dots, it starts to taper off over here on the right. And what's going to end up happening is it's going to continue to level off and never actually cross over the y equals 2 boundary line. Let's go ahead and draw that in. All the way across from left to right. Y equals +2 is our asymptote, and then everything is above it. That means for our range, k of x is always going to be greater than 2. And that's graphing exponential growth and decay functions.